Hello, we were on this part of our revision videos on solids, liquids and gases, and with just done density and the idea of measuring volumes of irregular solids. We did a little example here of a calculation featuring density and about the units and the way in which you can describe what the density is in words. We looked at the symbol, which was rho, and we discussed that you can leave density in grams per centimeter cubed or in kilograms per meter cubed, depending if the question gives you the numbers in one or in the other. Most the sort of the standard one is this one, but you find many tables in physics where they give you the densities in grams per centimeters cubed, so they're both absolutely fine. We did an example here with aluminium. We found that the mass of 1 kilogram of aluminium, of 1 meter cubed of aluminium, was really high, 2,700 kilos. Quite big. It makes sense. That's quite a light metal. If you did the same thing with lead, find a much bigger mass. We talked about how to measure the volume of one irregular solid using a displacement can and a measuring cylinder. So all of that was in the previous video. If you haven't seen that, then go and see it, and then come back to the second one now. So here we're going to talk about pressure and fluid pressure, and maybe we get time to talk about changes of state also. So let's get on with pressure to begin with and see where we end up. Alright. So the best way to understand pressure, as with many other ideas in physics, is to look at the equations. They tend to explain things quite well. So pressure is has a symbol of a P, but it's a small p. Most people write it as a big P, like if they wrote pressure next to volume it would look like that, but that's not right. It should be that pressure is small and volume is a big letter. Okay, so we have to be careful with those. So pressure is a small p, and the formula for pressure says that it is equal to the force divided by the area. Okay. Now this idea of force over area applies as much for a force like if you could be pressing with your hand on a particular part of a, I don't know, on some piece of wood, and the piece of wood had if you looked at it head on, it looked like this, and it had a length of 2 meters cubed up and 2 meters cubed up, a length of 2 meters cubed. That is not physics. Length of 2 meters and width of 1 meter, for example. Then the area of this would be 2 times 1, right? So that would just be 2 meters squared. So the idea of pressure applies to a force applied onto an area like this, so that if this force was 100 newtons, and if you were gonna work out the pressure, it would just be force divided by area, which is 100 newtons divided by an area of 2 meters cubed. So the pressure would be 50 pascals, which is the unit of pressure. A pascal is the same thing then as a newton per meter cube squared, right? Newton from the forces and meter squared for the area. Now pressure doesn't only apply to things like this where you have a force applied on a surface of some kind. It also applies to when you have a container like this, and inside you could have an orange gas, why not, inside of the container. And as the particles of the gas run around really quickly and they press on the sides of the container, then every time they hit it and they change direction, they're exerting a force on that surface. So that force can also be averaged out for all the particles, and we also call that the pressure exerted by that gas. Okay, and you can also have it with a liquid. You can have a container like this, and you can have the let's say that it's a golden liquid of some kind. The liquid is going to also, because of its attraction by the earth to downwards, it's also going to exert a certain amount of pressure on all the surfaces of the container. It's going to push on the container in that way, and it's going to push in the container in this way. And as you go deeper and deeper and deeper in liquids, the pressure will get bigger and bigger and bigger because there's more liquid above it, so there will be a higher pressure on something this high of liquid compared with this high. And so if you go to the bottoms of the oceans, that's why they're not very much explored yet, the pressures get really huge, and you need very strong structured submarines to be able to get to go down that far. Anyway, so that's a brief intro and reminder to a few of the ideas that we talked in the past about pressure, and it's interesting to note that it's such a it's a very important idea because it applies to all of these different circumstances. It doesn't just apply to when you're pushing with your hand on a surface or anything like that. Okay, so having said that, let's look at the triangle just as a reminder for how you would usually remember this equation if you rely on triangles for these things. So what's got to be at the top? The force, right? This guy's got to be at the top. So we put the force here, and the pressure and the area, as I said in the last video, doesn't really matter the order in which you put these two at the bottom, because 3 times 4 is the same thing as 4 times 3. They're both 12. So it doesn't matter if you multiply this first or that first. Now, we mentioned that the units for pressure were pascals. Okay, so I'm going to write it here, pascals, and 1 pascal was the same thing as 1 Newton per meter squared. They were exactly the same thing. Newtons per meter squared are the same thing as pascals. So that's important to know. If you ever forget what a pascal is, you just write the equation for pressure and you say, well, it's force over area. Force is in newtons, you should know that, and the area is in meters squared, so that will be able to help me remember that 1 pascal is 1 Newton per meter squared. Whenever you forget anything about a particular quantity in physics, the best thing is to look at the equations and to have a look at what's there, and as you become familiar with them, then you won't forget the units and that kind of thing. So let's do an example question, which is always the best way to understand something. So a question could say, what is the pressure? The word that they always use with pressure is this one, exerted or applied. What is the pressure exerted by a girl who has a mass of 60 kilograms on the floor, if she happens to be wearing, so if she's wearing stiletto heels of surface area 1 centimeter squared. Okay, so that's a pretty small area. It's about this on your screen. It's about this area, and if all her weight was on that area, what would be the pressure exerted? That's what the question is asking. Now, first thing to notice is that this is a simple pressure calculation, in the sense that you only have to use the formula for pressure is equal to, if you cover this up, then you get force divided by area. So in that sense it's quite simple, but there's a complication there's a couple of complications. First of all, we don't have the force, right? This is not a force, this is a mass, so we can't put 60 in here as the force. We've got to change that into a force. And second of all, and we need the force in newtons, and second of all, the area should be, if we're going to use newtons, the area should be in meters squared, and this is in centimeters squared, so there's going to have to be here a change of units, and hopefully this video will serve you also as a little bit of revision on how to do that. So let's do first things first. Let's convert the 60 kilograms to a force. So first thing to do, convert 60 kilos to newtons. Okay, and so I'm going to draw a plan here. What's the second thing I'm going to do? Second thing is to convert centimeter squared into, so 1 centimeter squared, which is the one that I have, I need to convert it into some amount of meters cubed, meters squared. So I need to know this and I need to know that. Once I do these two things, then I'm fine to just use the formula that pressure is equal to force over area, and I can get my answer in pascals. Okay, so now we have a plan of action, we can get going. What is the first thing to do? Well, kilograms, to go into newtons, we need to use the very important formula that weight, which is a force, is equal to the mass of something times the gravitational acceleration, which is 10. So the mass is 60, we multiply it by 10, which is the gravitational acceleration, we get a weight of 600 newtons for the girl, and we can now, we have half of the job done of the conversions. Second of all, centimeter squared to meter squared. I always recommend that you do the thinking in this way. If you want to go from centimeters to meters, the number that takes you from a centimeter to a meter is always 100, right? And since this is 1 centimeter squared and we're going to go to a meter squared, then it's always 100 squared. If the answer was cubed, if this was volumes, so this was cubes to cubes, then it would be cubed. But being squared, this is squared. And the final thing to decide is whether we're going to divide it or multiply it. So we have 1 here. Are we going to divide 1 by 100 squared, or are we going to multiply 1 by 100 squared in order to write it in meters squared? So here, I'm afraid the common sense is the best way of doing it, so you need to think a little bit about it. So if my number is initially expressed in a small unit here, centimeter squared, and the volume stays fixed, sorry, the area stays fixed, so the area of her stilettos is fixed to 1 centimeter squared, and I want to express the same area here as multiples of this guy, which is much bigger. A meter squared would be like, you know, much bigger than the screen. It would be like huge compared with this amount. If I want to express it in units of this, then it's going to be a much smaller number of these than it is of these, right? Even 10 of these would be a fraction of one of the big ones. So I'm not going to multiply by that, I'm going to have to divide by it, and that's going to be the key, to divide by that, so I don't lose marks there. A lot of people do the conversion of units, they think, well, a meter has more than centimeters, it's bigger, so I'm going to multiply, but no, you have to divide it. Hopefully that makes sense. A meter squared is much bigger than centimeter squared, so the same area expressed in a bigger unit would be a smaller number of those guys. So if I do that, if I divide 1 by 100 squared, I get that 1 centimeter squared is equal to 0.0001 meters squared. Just for a bit of revision on standard form, this is the same thing as 1, 2, 3, 4 zeros, including the one before the dot, so this is the same thing as 1 times 10 to the minus 4 meters squared. The 4 comes from these 4. So in other words, if you had 0.002, that would be the same thing as 2 times 10 to the 123 minus 3. And so forth. And if you had 0.025, for example, that would be 2 times 10 to the, sorry, that would be 2.5 times 10 to the 2.5, right? Times 10 to the 2 minus 2. So in that case you wouldn't necessarily write it because it's a very small number, but anyway, hopefully that's a bit of revision in standard form. So that would be your answer in meters squared. And so now you can do the calculation. You say, well, pressure, I'm going to do it up here because I'm running out of space. So pressure is equal to force over area, which is 600 divided by 0, well, divided by 1 times 10 to the minus 4, or just 0.0001, and that is equal to, comes out to a pretty big number, 6 with 6 zeros, so it's 6, 1, 2, 3, 1, 2, 3 newtons per meter squared, or pascals, and that is the same thing as 6 times 10 to the 1, 2, 3, 4, 5, 6 pascals. 6 million pascals. That's how much force a girl wearing stilettos would apply on the how much pressure, sorry, she would exert on the small area she's pressing on. And this is why when they step on you, if you're dancing or whatever, and somebody steps on you with stilettos, it can really break your toes quite easily. The idea of pressure is useful because you could have an elephant which has 4 huge legs, and even though the elephant weighs a couple of tons, much more than the girl, if the legs are this fat, so this wide, the base are this wide, they have a lot of area, then the pressure exerted by the elephant is much smaller than the girl who's just wearing these really sharp stiletto heel kind of shoes. The pressure exerted here is bigger than it would be with the elephant. And the idea of pressure expresses that idea. This is a pretty silly sentence, but anyway, you get the idea. And the and the idea of density we were talking about before expresses the idea that even if you have one thing that it might be a much bigger volume than another, still this smaller thing could have a larger mass than this one, because the density of this is much higher than here, right? And the idea of density is really well understood by the example of a neutron star. Neutron star it's made of neutrons completely, and the neutrons are in the middle of an atom, so they're incredibly close together and very, very, very tiny. And the density of even the densest things that we know, materials, are still very low density because they're in the middle of a really empty atom. But if you had a star made of just neutrons, where you didn't have the space around the atoms, you just had, you could imagine it as lots of nucleuses of atoms close together without the electrons around them, and without them having to shape into atoms that are really spaced out. They're just everything compacted together as neutrons. Then a single spoonful of that material would weigh several times more than the Earth. So that's how dense the nucleus of an atom is, and that's expressed really well by the concept of density. While the one of pressure explains why this can happen, bigger pressure by a really light person compared with an elephant, the idea of density expresses that. Okay, we need to know also about some applications of the idea of pressure. So an application would be, for example, the idea of skis, or the invention of the skis. Skis have a really large area, and the idea is to spread the force so that you get a low pressure. That means that you won't sink into the snow. Basically, you won't cut into it, you can just slide over the surface. So for some invention, or for some applications, we want low pressure, like in skis, and for others we want high pressure. When do we want high pressure? For example, with a pin, or drawing pin. Drawing pin has a large surface like this, so that you can apply pressure with your finger, but then it's got a very sharp tip, so that when you try to pin through a wall or through a piece of paper or whatever, then all of your force that you're applying onto this larger area is now concentrated in this very small area, so the pressure is very high. So this would be a small area. Force is then concentrated, so not spread out, and this therefore would be a very high pressure, right? So you need different ideas for these two. You've also seen this with like those rackets that people wear on their feet when they go to the North Pole and everything. These rackets are meant to increase the normal surface of your foot. If your foot is normally got this area, then the racket increases that, so that the pressure is much lower, and you won't fall through little cracks in the snow or the ice where you're walking that might be there. And if you had a higher pressure, you would just go through them. The racket allows you to spread the force out like that. Okay, so we didn't make it to fluid pressure, but we'll talk about that and the next ideas in the next video.